These are notes on nuclear reactions, which is chapter 25 in your book. Normally I wouldn't teach nuclear reactions until after we've done chemical reactions, but given the amount of time left in the semester, I think it makes more sense to do nuclear reactions now and chemical reactions starting second semester, since that's a larger topic. But that's why we're kind of jumping around in the book a little. Nuclear reactions are reactions that take place in the nuclei of atoms. So, unlike chemical reactions or physical changes where the atoms themselves stay the same, nuclear reactions, the word nuclear comes from the nucleus, those take place inside the nucleus of an atom, meaning that the atom itself changes, the element changes, because remember, elements are based on the number of protons, which are part of the nucleus. So if you're changing the nucleus around, you're most likely changing the actual atom. There's sort of two branches, I would say, of nuclear reactions, or two types. One is radioactivity, so that's particles within the nuclei of atoms changing, so protons changing, neutrons changing, or maybe just particles leaving. So maybe no particles change, but they leave the nucleus, and that changes the element. That's primarily chapter 25, section 1. Then there's also fission and fusion, which are the two I think a lot of people think about when they hear nuclear reactions. And that's splitting, that would be fission, or combining, that would be fusion of entire nuclei. So fission would be the splitting of a nucleus. Fusion would be the combining of entire nuclei. And in either case, you're changing the number of protons, and so again, you're going to change the element. And that's primarily in chapter 25, section 3. So if we want to look at a kind of comparison of nuclear, physical, and chemical changes or reactions, we usually say reactions for nuclear and chemical, but changes for physical. It kind of breaks down like this. And now I'm noticing that it says chemical changes. Either way, you can say chemical reaction or chemical changes. So I'm going to sort of summarize this. You're certainly welcome to stop the video and write all of this down. I'm not going to go through bullet by bullet, but I'm going to summarize it overall. You can also do this as like a triple Venn diagram. That would be another really good way to organize this. So nuclear reactions, you have a change in the nucleus, which I said earlier, and that results in the change of the element. The actual element changes in a nuclear reaction. So you might start out with, let me see if I can remember one off the top of my head, uranium, say, and through a series of nuclear reactions, you end up with lead in the end. So you go from uranium to lead, completely different element. Physical changes in chemical reactions, there are no changes in the elements. The elements stay the same. Whatever elements you started with, you end up with in the end. Nuclear reactions, there's no way to speed them up, slow them down, or stop them. They happen very naturally. You can get more to happen, but you can't speed up the actual reaction. So for example, if you have a lot of uranium, you can cause a lot of fission of different elements or of different atoms, such as in a nuclear bomb, but you can't speed up that reaction or slow it down or stop it. Once it starts, it proceeds, and these happen naturally. Actually, physical and chemical changes also happen naturally, and that's the last bullet on physical and chemical changes. Those can both be affected by what are called catalysts. And catalysts are things that speed or slow reactions. So a catalyst we're all kind of used to is temperature. If you add energy to, say, melting ice, it speeds up that physical change of the ice melting. There are certain chemical reactions that if they take place in the presence of heat, they progress a lot faster than others. There are certain compounds in chemical reactions that if you add them, they don't affect the reaction itself, but they speed up the reaction. And conversely, you can add things or take away things that slow down reactions. So nuclear reactions aren't affected by catalysts, whereas physical and chemical changes can be. In a nuclear reaction, large amounts of energy are often emitted, usually emitted. That's why, for example, in a nuclear bomb, you get so much energy because you've got nuclear reactions going on. Obviously, energy can be emitted in both physical changes and chemical reactions. Again, going back to a topic we just studied, we saw during phase change, for example, when something is condensing or when it's freezing, it gives off energy because it no longer needs that energy in order to be in a liquid state if it's becoming a solid, or a gas state if it's becoming a liquid. So the reverse of melting and boiling, which we really focused on, that takes energy to do. We know when we froze our lauric acid, it gave off energy. It gave energy to the surrounding water that it was in. So physical changes and then chemical changes as well. If you think about like one of the instant heating pads that we use skiing or sledding, that's obviously a chemical change that's giving off heat, but those aren't massive amounts of energy. Something else with nuclear reactions is that they don't always follow the law of conservation of mass. So that idea of whatever mass you start out with is the mass you end up with isn't necessarily true in nuclear reactions. You actually have a conversion often of mass becoming energy. So earlier in your schooling, you may have learned that everything is matter except energy. I think Bill Nye even says that in one of his earlier videos. In nuclear reactions, you can actually convert matter to energy. And that's what that famous Einstein E = mc squared equation talks about, that m is the mass, and E is energy, and C is the speed of light squared. So it takes a very little amount of of mass, multiplied by the speed of light squared, and you get a massive amount of energy, hence the large amounts of energy emitted, but you also get a slight conversion of mass to energy. And we'll talk a little bit more about that later, but we're not going to go into too much detail on that. Some differences between physical changes and chemical changes is that in physical changes, and that's the second bullet here under physical changes, is there are no changes in the compounds or the molecules. So whatever you start with, if you start with H2O in a solid form, you end up with H2O in a liquid form. Or maybe you start with a large sheet of H2O in solid form, or a large sheet of ice. My daughters were doing this today. They found a bunch of ice and they were breaking it up and then puzzling it back together. That's a physical change. You haven't changed the water at all. It's still water. It's water the entire way through, whether it's melted, whether it's in a million pieces, whether it boils. It's always water. It doesn't change how those elements are bonded together. It doesn't change the molecules. Compared to chemical changes, they don't change the elements, so there would still be there would still be hydrogens and oxygens, but maybe it decomposes the water into hydrogen gas, H2, and oxygen gas, O2, so that you have the same elements that were always there, the hydrogens and the oxygens, but now they're bonded differently. You have two separate things, hydrogen gas and oxygen gas, compared to before when you had water, H2O. And some people have picked up on the fact that H2O, how could that become H2 and O2? Because it seems like you'd be missing an O. And that's one of the things we're going to cover when we talk about chemical changes. So let's look first at radioactivity, which is in 25.1 and 25.2. So I like to say radioactivity stabilizing isotopes since the 1890s. Radioactivity is actually a natural phenomenon. It's been around as long as elements have been around. But it was in the 1890s that we actually discovered radioactivity. And the idea is, of all of the isotopes we know of, which numbers, boy, I want to say in the thousands, only several hundred of them are stable. And so and when we say stable, we mean able to exist the way they are. All of the other ones undergo some sort of radioactive decay to make them more stable. Think of it as radioactivity is therapy for isotopes. They're not very stable, so they go to therapy, and they become more stable. They emit things. Some of them will take on things, just like, if something is going wrong in our life, we might give up something or take on something new, and it makes us a little more stable. So all of this, remember, happens in the nucleus. So particles in the nucleus are held together by the nuclear force. It's an extremely strong force, but it only operates over small distances, and it attracts protons and neutrons to one another. Notice that if you just look at electrical forces, protons, because they're both positive, should repel. But the strong force is strong enough that at very small distances, it can overrule. It's stronger than the electrical force. And so the nuclear stability kind of depends on a ratio of protons to neutrons. In small atoms, it's about a 1-to-1 ratio. You'll notice that in the smaller atoms that the average atomic mass is about double the number of protons, because there's about double the number of nucleons, or there's the same number of neutrons plus protons added together. And so it's about a 1-to-1 ratio. But as elements get larger and larger, their nucleus gets larger, and they need more neutrons than the same number of protons. Because remember, the nuclear force only operates over small distances. So as that nucleus gets bigger, it's harder for the nuclear force to overcome the electrostatic force of those protons repelling. That's a lot I just said, so if that doesn't make sense to you, either look it up in your book, a great resource, or make sure to ask about it in class. Here's a graph, which I think is also in your book. I got this one offline, that sort of shows, it's a graph of nuclear stability. So the number of protons are on the bottom, and let's see, let me get a pen here. So the number of protons are here on the bottom. The number of neutrons are on the y-axis. And this red line here is neutrons and protons equal 1. So you can see down here in the smaller elements up to about, element 19 or 20, somewhere around here, okay? The number of protons equals the number of neutrons, more or less. But then as the elements get larger, okay, so, we've got, here at, say, 40 protons, you're going to have approximately 50 neutrons. Here, when we get up to, say, 70 neutrons, you actually end up, 70 protons with 100 neutrons. So this is where you're going to be most stable. So the more protons you have, so the larger elements, the larger that ratio of neutrons to protons is going to be. And here they've got, neutrons divided by protons. So depending on which way you put the ratio, it's going to be either larger or smaller. All right. So again, this graph comes from your book as well. It's a slightly different in your book, though. All right. So let's talk about different types of radiation. And there are 3 main types. And then your book talks about several others, which I'll kind of bring in here and there. So alpha radiation, which is actually a particle, is the first type. And generally people list it as the first type because it's the least harmful to humans. Alpha radiation, an alpha particle, is essentially a helium nucleus. If you think about helium, it's atomic number 2, meaning it has 2 protons. It also has 2 neutrons, and so it has a 2+ charge. So an alpha particle has a 2+ charge, and it really is just a particle of 2 protons and 2 neutrons. It can be stopped by a piece of paper. And throughout these different types of radiation, I'm going to tell you what things can stop them. Obviously, the things that are stopped by little things like a piece of paper are the least damaging to us. However, alpha radiation, it's not too damaging to us in the environment. And as I talked about earlier, radiation is natural. It happens over time in lots of different things. And so we can't completely avoid radiation. So there is alpha radiation in the environment, but it can be stopped pretty easily. It doesn't harm us. Where it can harm us is if for some reason you would ingest something, eat something that gives off alpha radiation. And in that case, there aren't a lot of things in so it can be easily incorporated into your body, let's say that, and then it can be damaging. The symbol for an alpha particle is this, So the He, if you go back to remembering your symbols from way back when, He is for helium, because remember, it's a helium nucleus. The 2 is the number of protons, so that's that 2. And then the 4 is the protons plus neutrons, so that would be 2 plus 2 is the 4. And so this is the symbol for the helium nucleus, or I'm sorry, for an alpha particle. So this is then what we would write as a reaction. So here we have the isotope uranium-238, and so uranium has 92 protons, and then uranium-238 has whatever 238 minus 92 is. Let's say that would be 6, 23 minus 9 would be, 14, so 146 neutrons and 92 protons. And so this is uranium-238. It's a radioactive isotope of uranium, and that naturally decomposes into thorium-234 plus a helium nucleus. So if you notice a couple of things here about the math. Okay, so the 92 here, if that loses the 2 protons, that gives you 90 protons. 90 on the periodic table, and I would look at a periodic table, is thorium. But the 238, that is, it's lost 4 protons plus neutrons. Okay, so 2 of those were protons, and then 2 were neutrons, and so that 238 minus 4 is thorium-234. And so that becomes an isotope of thorium plus the 1 helium nucleus or alpha particle that it has lost. All right. The next type of radiation is called beta radiation, and beta radiation is also a particle. If you think about the Greek alphabet, it goes alpha and then beta, which, by the way, is where the word alphabet comes from. Alpha, beta, alphabet. Just a little random trivia for you. So beta radiation can be stopped by like a piece of aluminum foil or wood, also not as damaging, but more so than alpha radiation. In beta radiation, a neutron becomes a proton and an electron is emitted, is given off. And that emitted particle, that electron, is the beta radiation. And so beta radiation then is negative in this case because an electron is negative. There's actually, if you look more deeply into beta radiation, there's actually another type of beta radiation, and I'm going to mention that. Your book calls it something a little different. It really depends on what source you look at, and so we'll talk about that in a minute. This then is kind of what the process of beta radiation looks like. So we've got a neutron. So the N is for neutron. We're going to put a 0 here because there's no protons in a neutron. But this number, remember, is the mass number. It's protons plus neutrons. And so there's 1. And by the way, when we talk about mass number, that's why beta radiation can penetrate more, because it actually has less mass than an alpha particle. So it can penetrate more deeply. If you think about something with more mass, if you go back to your knowledge of physics, is going to have less acceleration, and so you can stop it with less force. Those of you who took physical science remember that whole idea of F equals ma, meaning the less mass, the more acceleration, meaning the more force is needed to change its direction. So one neutron becomes essentially a hydrogen nucleus. Hydrogen is the only element that naturally exists without a neutron in it. And so here we have hydrogen, and the 1 stands for the 1 proton. That's the neutron becoming a proton. And then we also get 1 electron. And so the electron is given off. This is the electron. And so the -1 here actually stands for the charge. And then the 0 is because there are no protons or neutrons. So keep that in mind. This is a little different. This is a -1 charge. And so A reaction that undergoes beta decay would be carbon-14. Carbon-14 is a naturally occurring radioactive form of carbon. It's in any living thing, including you and me. And carbon-14 is what scientists track when they're dating a fossil. So when they're saying, we found this fossil and it's this many million years old, what they're doing is they're tracking the decay of carbon-14. We're going to talk about that in a few minutes. So carbon-14, carbon has 6 protons. It has 8 neutrons, so 6 plus 8 is 14. And so one of those neutrons is going to become a proton. And so you don't change this number here because you have the same number of neutrons plus protons. But if one neutron becomes a proton, that now changes the element. You now have nitrogen, and it's nitrogen 14, plus, remember, an electron was given off in the process. There's another type of beta radiation, and it's some sources that you look at will list it as beta positive and beta negative radiation, in which a proton becomes a neutron, so the other way around, instead of a neutron becoming a proton, and what's called a positron is emitted. And a positron, if you've heard of antimatter in any science fiction book you've read, a positron is actually antimatter. It is an anti-electron. It has all the properties of an electron, but exactly opposite of it. And there's some pretty cool things that happen with antimatter. If you look on my website, I've got some really great resources that explain antimatter in a very student-friendly manner. This is also called positron emission, and so you'll see that in your book. So that's why I'm saying some resources will list it as a type of beta radiation. Some will list it as something separate, which is called a positron emission. And basically, if you go back to that first slide where we talked about how, or maybe it was the second slide, where we talked about how the stability of a nucleus depends on a ratio of neutrons to protons. Basically, if you think about beta radiation, if the atom has too many neutrons, it's going to undergo this first type here, where the neutron becomes a proton. That will get rid of a neutron and add a proton. But if the atom doesn't have enough neutrons, has too many protons, then it would undergo this one, where the proton becomes a neutron, and that gets rid of a proton and adds a neutron. So what type of radiation something undergoes kind of depends on what it needs to do. How is it going to get that ratio of protons to neutrons to a stable number? And then finally we have gamma radiation. And gamma radiation is not a particle. If you go back to the electromagnetic spectrum, gamma radiation is on the high energy, high frequency, short wavelength side of the electromagnetic spectrum. And gamma radiation is a high energy photon. A photon is essentially a packet of energy. Some of your scientist projects talked about photons, and it's the highest energy electromagnetic radiation. It has no charge because it's a photon, it's energy, it's not a particle, and it's only stopped by lead or several even feet of concrete for the most part. Okay, nothing can completely stop gamma radiation, and it's incredibly damaging to human tissue. This is why, so if you think about the electromagnetic spectrum, or if you were thoughtful enough to suddenly look one up quickly, you'll notice that X-ray radiation comes right before gamma radiation. Both of these are known as ionizing radiation, and they're incredibly damaging to human tissue. This is why when you go to the dentist and you get your X-rays taken, they put that heavy lead vest on you, and they actually leave the room, you'll notice. But that lead is designed to stop the X-rays from getting at your vital organs, so that the X-rays are only penetrating into your mouth, which still isn't fantastic, but neither are cavities, so it's kind of a trade-off. So here's an example of gamma radiation. So this little symbol here, that is the lowercase gamma. And depending on what font you choose, sometimes you'll see it more of like a Y, sometimes you'll see it with this little swishy thing and a little loopy thing down here. Again, it kind of depends on the font you chose. And so here's thorium-230. So thorium, as you may remember from an earlier reaction that I showed you, I think with alpha radiation, has 90 protons. And this is thorium-230. And thorium-230, by alpha decay, degrades into radium-226. So the 2 protons that were lost that are here account for the 88, so that makes it radium. And then there's 4 protons plus neutrons, 2 neutrons, 2 protons. And so that changes the 230 to 226, and that's alpha decay. But then in addition to that, there's also some gamma radiation given off. And that's what makes this kind of decay so harmful. So that's why early people working with radiation who didn't really know what it was so often got cancer and often died. Not because of the alpha radiation that would be given off, but because of the gamma radiation that's given off in addition to the alpha radiation. So let's talk briefly, because I mentioned it before, about radioactive dating. And this again is where you hear scientists say, you know, this rock is this many millions of years old, or this fossil is this many years old, or whatever. And it has to do with tracing how radioactive elements have decomposed, decayed over time, because they do it in a very regular manner, and we'll look at that in more detail in class. So what radioactive dating does is it uses radioactive decay of certain elements to tell the age of a rock or a fossil. A fossil being something that was once living, so in that case they're tracing carbon-14. A rock, generally they're tracing natural uranium that's in the Earth's crust. That's where we get our uranium. It's a naturally occurring element. And so what you need for that is a half-life. It's the amount of time it takes for half of an amount of an element to decay. So for example, radium-226 has a half-life of 1,620 years. So if a fossil starts with 1,000 grams of radium-226, in 1,620 years, it will only have 500 grams left. Now, some people get confused and they say then in another 1,620 years, it will have none left. That's not true. It has half of whatever was left before. So in another 1,620 years, it will have 250 grams left. In another 1,620 years, it will have 125 grams left, and so forth and so on. And notice if you keep cutting things in half, you're going to get smaller and smaller and smaller amounts, but you actually never reach zero. And at some point, would all of the radium-226 decay? Absolutely. But keep in mind how many actual atoms there are in, say, 1,000 grams. You could actually convert that. You could say, okay, I've got 1,000 grams of radium. Radium has an atomic mass of about 226 moles per gram. So you can figure out how many moles, and then there are that many atoms, 6.02 times 10 to the 23rd atoms in 1 mole. That's going to be a ridiculous amount. So eventually, yes, all of the radium would decay, but it's going to take billions of years, more time than we need to worry about. One of the things about radioactive dating with rocks is if you go back to your knowledge of the rock cycle from 7th grade or whenever you did kind of catastrophic events, that whole unit, is that radioactive dating of rocks dates to when that rock was last an igneous rock, so coming out of a volcano. If it then is weathered into sedimentary rock and then at some point goes back into the mantle and remelts and then spews out again, then the dating starts over. The life starts over, essentially, if you think about the life cycle of a rock. So while there's no necessary beginning of the life of a rock, I would say as far as radioactive dating, if you're telling how old a rock is, the beginning is when it solidified as an igneous rock. When we're looking at carbon dating of fossils, we're looking at the time from which that fossil died. Because you're constantly making new cells and growing, and so the ratio of carbon-14 to carbon-12 in your body stays relatively the same whenever you're alive. But once you're dead, that carbon-14, you're no longer adding carbon to your body, and the carbon-14 starts to decay, and so then they can start to look at, okay, we can tell when the carbon-14, we know what the original ratio is, we know what the ratio is now, we know how quickly carbon-14 decays, so we can tell when this thing was living. And since when we're looking at fossils, we're looking at thousands or tens of thousands, or even sometimes millions of years, whether that living thing, whether it was a plant or an animal, was alive for 50 years or 100 years or even 200 years doesn't really matter. One thing is, the shorter the half-life, the greater the radioactivity. So radium-226 has a half-life, as we said, of 1,620 years. Uranium-238 has a half-life of 4.5 billion years, meaning radium-226 is much more radioactive than uranium-238, which we're going to talk about this a little more later as far as nuclear fission and fusion. That'll be our next set of notes. But a lot of us think, well, but uranium, isn't that so radioactive? Isn't that what we use in bombs? Why wouldn't we use radium? It seems more radioactive. Remember that that's natural decay. So if you took a chunk of uranium and set it down in the middle of a community, obviously you wouldn't want to be around it anyway, but it would take billions of years to decay, for half of that uranium to decay. 4.5 billion years to be exact. That's not what's happening with an atomic bomb. With an atomic bomb, we're using the process of nuclear fusion to bust that uranium apart. So that's a different process than this natural decay that we've been talking about. All right, please make sure if you have questions, you put them online, or please write them down. For those of you who say, I like to do notes in class because I can ask questions, your chance to ask questions is tomorrow in class. So please write them down so that we can get to those questions. Have a good night.